see these eigenvalues and eigenvectors of that applications also. So in continuation of these concepts, so today we are going to see the Kelly-Hamilton theorem. One theorem in these eigenvalues and eigenvectors. It is very important theorem and it has very wide applications, where particularly we can find out the inverse of the matrix very easily, as well the power of the matrix. Before going to the Kelly-Hamilton theorem, we would like to see some of the basic inputs for that we may be called as matrix polynomial. Know anybody that matrix polynomial? We have seen the polynomials and then variable say x, a pn of x. That means k naught plus a1x plus a2x square plus so on plus an x power n, right? Where an not equal to 0. This is the polynomial in x of degree n, right?
Yes, sir.
Where all the coefficients a0, a1, a2, a3, so on, an are the coefficients. Suppose in place of the coefficients, if they are the matrices, capital A0 plus capital A1x plus capital A2x square plus so on plus capital an x power n. Okay, so then it is said to be the matrix polynomial. Understand? If a general polynomial in x is extending into the polynomial with the coefficients of matrices, then it is said to be matrix polynomial. Okay, all the matrices a0, a1, a2, a3, so on, an. And also these matrix, any square matrix. Now let us, I hope you have been understood that matrix polynomial, right?
Yes, sir.
The matrix polynomial. I will write it here so that you will be understood. That matrix polynomial, suppose a0 plus a1x plus a2x square plus so on plus an x power n. Okay, where an is non-zero matrix. So therefore this is said to be the matrix polynomial all these a0, a1, a2, a3, so on, an are the matrices of order n by n, square matrices of order n by n over the field f. It is called the matrix polynomial of degree n. Okay, so here one thing I would like to explore you here, it is, suppose any matrix, any matrix, if you consider A is equal to, in which suppose one element is a polynomial, of degree n. Understand please, one element is a polynomial of degree n.
Sir.
There are elements are there, right? Hello? Somebody is asking something.
Yes,
Am I
sir.
audible, students?
Yes, sir. But if he innocent.
Huh? Sorry?
Innocent.
Mrityunjay, what do you want to say?
Well, it is here नहीं है.
Is not visible my document?
Visible, sir. Yes,
Visible.
sir.
You just refresh your system or re-login, please. I think your side there may be a network issue. I think so. So other people are visible, right? Yeah. So here you see, suppose a matrix, it has entries. There may be of order n by n, whatever it is. It is not the concern. But suppose if you consider any one of the element is a polynomial in n of degree n, then this matrix can be expressed into the matrix polynomial. Understand the point? Every square matrix, the point is every square matrix whose elements are polynomials in x of maybe degree n can be expressed as a matrix polynomial in x of degree n. X of degree n. Okay, where n is the highest power of x. So understand, please. So maybe it is not required all the elements are polynomials of degree n. There may be at least the highest degree is n. That is. So therefore, such matrices can be expressed into the matrix polynomial like this. Suppose we can take it an example. Suppose the matrix A is equal to 1 x plus x square 0. Let us see. Yes, this is a matrix. So this matrix can easily to express into the matrix polynomial. You can see how we can express this into matrix polynomial. First write out here one entry, it has the degree 2, polynomial of degree 2. So therefore you write it this, all the elements. So therefore 1 plus 0 into x plus 0 into x square. This one 0 plus 1 into x plus 1 into x square. Here 0 plus 0 into x plus 1 into x square. Okay, last one 0 plus 0 into x plus 0 into x square. All of them we write it accordingly. So then we can make it this one as 1 0 0 0 into 1 or x power 0 plus x coefficients, you write it. What are the x coefficients? 0 1 0 0 plus x square coefficients. You can write it 0 1 1 0, right? So this is the matrix polynomial that is of form A is equal to the given matrix A is equal to A0 plus A1x plus A2 x square. You see, suppose the given matrix is having the elements or polynomials of degree n, then that matrix can be expressed into the matrix polynomial. This is matrix polynomial. In x of degree 2, right? Okay, this is what. So this statement will help you in the understanding of Cayley-Hamilton theorem. Now let's see the Cayley-Hamilton theorem. What Cayley-Hamilton theorem states that, so it is very important. they will be asking you the question as state and prove the Cayley-Hamilton theorem like that. So you only to state the theorem and you only to derive the theorem, prove the theorem. So therefore, what the statement of the Cayley-Hamilton theorem says that every square matrix A of order n satisfies its own characteristic equation. Satisfies its own characteristic equation. Please see it here. Every square matrix A of order n satisfies its own characteristic equation. What is meant by characteristic equation? What is the characteristic equation is?
Sir, A by lambda I is equal to.
What is the characteristic equation? Determinant of A minus lambda I is equal to 0, right?
Yes, sir.
That results in a polynomial in lambda of degree n. So where that lambda is any scalar, okay? If there exists a non-zero solution for the matrix equation Ax is equal to lambda x, then x is said to be the eigenvector corresponding to the eigenvalue lambda. Okay, in such case that a characteristic equation can be derived that determinant of A minus lambda I is equal to 0. Okay, so therefore consider A is the square matrix and its characteristic equation is determinant of A minus lambda I is equal to 0. So therefore that determinant of A minus lambda I resulting in a polynomial in lambda of degree n that has the terms like this: lambda power n minus c1 into lambda power n minus 1 plus c2 into lambda power n minus 2 plus minus so on, minus 1 whole power n minus 1 into cn minus 1 plus minus 1 whole power n into cn is equal to 0. So that determinant will be giving you like this form, okay, where all the cn's are constants. Okay, this we can re-alter that equation is a polynomial in lambda is this characteristic. This is the characteristic equation, right? So what the theorem, Cayley-Hamilton theorem says that this characteristic equation is satisfies the own matrix, that is A. So therefore in place of lambda it is satisfying. That means lambda power n means A power n minus c1 A power n minus 1 plus so on minus 1 whole power n into cn into I is equal to 0. Right? This is the characteristic equation. The characteristic equation satisfied by its own square matrix A. This is what Cayley-Hamilton theorem says. So it has a very good applications, wide applications in finding the inverse of the matrix as well as power of the matrix. Let's see. Consider the square matrix A and its characteristic equation determinant of A minus lambda I is equal to like this: lambda power n minus c1 lambda power n minus 1 plus c2 lambda power n minus 2 so on minus 1 whole power n into, this is small c, not capital C. Tell me. Okay. Hello. Somebody is asking. Hello. Dear students, am I audible?
Yes, sir.
Yes, sir, you are audible.
Let's see. So you understood now that characteristic equation of the square matrix A, that is determinant of A minus lambda I, and it takes this form, that would be a polynomial in lambda of degree n, and take it as equation 1. Okay. So here we are finding the determinant of A minus lambda I. So therefore it has the cofactors. That cofactor matrix is the, what is the cofactor matrix? How we can define the cofactor matrix? Cofactors. What is meant by cofactor? Please tell me. Suppose if A is equal to A, B, C, D. What is the cofactor? Sorry, let us say 3 elements. Okay, so that it will be very clear. Three. Okay, let's take it here. This element, this the matrix. What is cofactors of the matrix? How we can find out the cofactor of the matrix? That means cofactor of first element. Let us say first one. That same row and same column deleted. The remaining matrix order. That means not order. That determinant of the remaining matrix. That is determinant of 2, 1, 2, 1, 2, 3. Right? 6 minus 2, 4. In place of 1, we can put it 4. That resulting you the cofactors. That each of the entry of the matrix can be calculated their cofactors. Okay. So here the matrix is there A minus lambda I. Since the cofactors of the elements of the matrix A minus lambda I are polynomials in lambda of degree n minus 1 or less. This point you would understood, I think. Clear?
Yes, sir.
Because A is, suppose if you take this a square matrix and A minus lambda I is like this, 1 minus lambda, 2, 1, 0, 2 minus lambda, 1, 1, 2, 3 minus lambda. This is A minus lambda I. Okay, for this example A matrix. Now the cofactors of the elements of this matrix A minus lambda I are polynomials in lambda of degree n minus 1 or less. Suppose if it is of order n by n, A is of order n by n, it results in you a polynomial in lambda of degree n minus 1 or less for the cofactors of the elements of the matrix A minus lambda I, right? Why? Because so one element, if you choose any element of this matrix A minus lambda I, you choose, the corresponding row and column will be eliminated. The remaining matrix determinant we are finding. So one lambda is out, the remaining will be n minus 1 lambdas. If you find out determinant, it will be giving you the order. That means the degree of the polynomial will be less than 1 of n, that is n minus 1 or less. Okay, understood? Right? So
yes,
each cofactor of the element of the matrix A minus lambda I are polynomials in lambda of degree n minus 1 or less. So therefore, the elements of the adjoint matrix, adjoint matrix would be defined as the transpose of the cofactor matrix, right? So therefore, this adjoint matrix have the elements, all are the polynomials in lambda of degree n minus 1 or less, right? The adjoint matrix have the elements as polynomials in lambda of degree n minus 1 or less. So hence, adjoint of A minus lambda I can be expressed because adjoint matrix have all the elements of polynomials in lambda of degree n minus 1 or less. So that this adjoint matrix, adjoint of A minus lambda I, can be expressed as a polynomial in lambda of degree n minus 1. That is a matrix polynomial with the matrices, the coefficients bi, we can say. So which are core matrices of order n. Okay, right? So that expressed here in the given equation 2, that adjoint of A minus lambda I is a matrix polynomial of degree, matrix polynomial in lambda of degree n minus 1. Okay, right?
yes, sir.
This understood? This step have you understood? because this is only the key step for proving the Cayley-Hamilton theorem. If you understood this, the theorem gets completed. Then everything, it is just simplification only. That adjoint of A minus lambda I have the elements or polynomials in lambda of degree n minus 1 or less. Therefore, it can be expressed as a matrix polynomial in lambda of degree n minus 1. This is the understanding of this step. That matrix polynomial, if you assume b1 lambda power n minus 1 plus b2 lambda power n minus 2 plus so on bn minus 1 lambda plus bn, because it is a polynomial, it resulting in you a matrix polynomial in lambda of degree n minus 1. Just that we assume like this. We don't know what is b1, b2, b3, so on bn. That can be find out of order n by n. Okay. So it is a matrix polynomial. Good. So once we have drawn that the adjoint matrix of A minus lambda A has the matrix polynomial in lambda of degree n minus 1. Now we can check it that the basic idea of inverse of the matrix, right? You know, inverse of the matrix A inverse is equal to, we can define that 1 by det A into adjoint A, right?
Yes, sir.
One by det A into adjoint A. A inverse is equal to 1 by det A into adjoint A. So therefore R, you can write it A into adjoint A is equal to det A into I, right? Right? So using this statement, we have A minus lambda, in place of A is, we have A minus lambda I into adjoint of A minus lambda I is equal to determinant of A minus lambda I into I. That is A minus lambda I, and adjoint of A minus lambda I will be a matrix polynomial that we have substituted here. That is equal to, we know determinant of A minus lambda I. That is the characteristic equation resulting you already expressed in equation 1. Determinant of A minus lambda is lambda power n minus C1, lambda power n minus 1i. Into I is there, we are multiplying with the identity matrix. C2 lambda power n minus 2i, so on, minus 1 whole power n Cni. Right? This is the equation we have drawn. Now we are comparing the coefficients of powers of lambda. So if you compare the coefficients of lambda power n in this step, this is the step A minus lambda I into this much is equal to this. So now we have to check it in the LHS. What is the lambda power n coefficient? If you multiply this lambda with lambda power n minus 1, then only it resulting you lambda power n, that is minus b1 into I minus b1, right? Right hand side, what is lambda power n coefficient? I. So therefore minus b1 is equal to I. Next, comparing the coefficients of lambda power n minus 1. This one, lambda power n minus 1, which will be obtained if we multiply A with lambda power n minus 1 into b1, A b1, okay, minus lambda with multiplying lambda power n minus 2, then it resulting u also lambda power n minus 1 coefficient. So minus b2, A b1 minus b2. This is LHS part where the coefficient of n minus 1 can be obtained. That RHS, what is lambda power n minus 1 coefficient? Minus C1 into I. This is like that. You can compare all the coefficients of the powers of lambda, lambda power n minus 1, lambda power n minus 2, like this. You can get it these equations. Minus b1 is equal to I, A b1 minus b2 is equal to C1i, A B2 minus B3 is equal to C2I, like that, so on. Here you see this is lambda power 0 coefficient finally. That means constant. Constant coefficient, you see what is the constants in the left hand side and right hand side. You compare that one, that A multiply with Bn. Then only it will be giving you constant, huh? A Bn is the constant in the left hand side, and right hand side the constant is only last Cn. Minus 1 whole power n into Cn. That is what we have here. A Bn is equal to minus 1 whole power n into Cn into I. Okay. So therefore, these are the resultant comparisons we have drawn by comparing the coefficients of powers of lambda. Now we multiply this, pre-multiply all these above equations by a power n. Pre-multiply with a power n. This is a power n minus 1 into a power n minus 2. Because you must understand what is pre-multiply. You have to multiply before, not the after. Because matrix equations, matrix multiplication follows the compatibility. Okay, pre-multiplication and post-multiplication. So that's why it is very clearly written that pre-multiplying all these equations by a power n minus 1 so on into I. Okay, so in such case, this will be multiplying with a. And adding all these, if you multiply this a power n, where it will be we have to multiply, it is not a power n, like it is to multiply with a. Sorry, it is not a power n, they were written a square, a cube, like this. No, a power n only, no? Right, sorry, I confused. A power n only. So multiplying with a power n minus 1, a power n minus 2, like. So now let it getting here that if you multiplying with pre-multiply with a power n minus a power n into b1 is equal to a power n into I, and adding that one, multiplying with this a power n minus 1 into a power n into b1, right? Here minus a power n into b1, here plus a power n into b1, we can get it, that will be cancelled. So like that, all the terms will be cancelled on the LH side. All of them will be 0. The right hand side only will be remain. The right hand side values are a power n into I, a power n minus c1 into a power n minus 1 plus c2 into a power n minus 2, so on, minus 1 whole power n, cn into I is equal to 0, right? This is what we have drawn. So finally, you see this, what is this equation? So it's very clearly, it satisfies the
characteristic equation.
Characteristic equation. A satisfies its own characteristic equation. This is what the Kelly-Hamilton theorem. So that implies A satisfies its, that is important, its own characteristic equation. This is important. Suppose some other matrix characteristic equation is not satisfied by A. A satisfies only its own characteristic equation. Okay, this is the Kelly-Hamilton theorem and the proof. Okay, now we see the deductions. That is what I have already explored you to find out the inverse of the matrix. So for finding inverse of the matrix, you pre-multiply with A inverse on both sides of this characteristic equation, where satisfies by A. So from this you can write it. So what is A inverse? Multiply with A inverse on both sides. So therefore here it will be A inverse remain, then remaining all other terms will be the powers of A only. So therefore this term you put it in the LHS side, and all other we can take it into the RHS side, where minus 1 whole power n into Cn into A inverse is equal to minus of all these A power n minus 1 minus C1 into A power n minus 2, right? If we are multiplying with A inverse, it will be decreasing power again 1, so on. So minus 1 whole power n minus 1 Cn minus 1 into I, right? Where last one A into A inverse become I. So therefore, so by using this one, A inverse is equal to, we can write it minus coefficient of minus 1 whole power n by Cn into this part. Okay, like that we can obtain the inverse of the matrix by using the Cayley-Hamilton theorem. And also we can obtain the power of the matrix. We can write it from this expression, A power n is equal to, we write it A power n is equal to, you take this part only into the LHS side, the remaining into the RHS side. That will give you C1 A power n minus 1 minus C2 A power n minus 2, so on, minus 1 whole power n Cn into I. This is A power n. We can obtain power of n, A power n, as well as obtain inverse of the matrix. These are the two applications of the Cayley-Hamilton theorem. And also there is one more. We can simplify the matrix equations, because sometimes it will be the matrix equations will be there. That matrix equations can be simplified very easily using these Cayley-Hamilton theorem. Okay, so this is the third application. So that third application we may be write it. We can simplify the matrix equations. Matrix equations. I will show you the problems here. Now the questions we can expect from this Cayley-Hamilton theorem, that verify Cayley-Hamilton theorem, that one type, and find inverse using Cayley-Hamilton theorem, find power of the matrix, the required power, by using the Cayley-Hamilton theorem, and we can simplify, or there is a matrix equation here. So here you see the question here, express this matrix equation as a linear polynomial in A. So we can, so therefore this total value we can express it into the linear polynomial in A. So therefore we can easily to solve that one. Okay, good. So these are the applications we can, that questions we can expect from the Cayley-Hamilton theorem. So for first part, so for verifying the Cayley-Hamilton theorem, for how we can verify the Cayley-Hamilton theorem, can anybody say? How we can describe the verification of the Cayley-Hamilton theorem of any given matrix?
Sir, firstly find the characteristic equation and put A in it.
Right. Firstly, we find out the characteristic equation and show that A satisfies its own characteristic equation, right?
Yes, sir.
If you prove that the characteristic equation satisfies by the given A, so the Cayley-Hamilton theorem is verified. That is, then finding inverse and power and all others will be same as it is using that one. Let's see. So the given matrix is A is equal to 1, 4, 2, 3. Now the characteristic equation of that A is to be determined. That characteristic equation is given by determinant of A minus lambda I is equal to 0. You find out that A minus lambda I, what is A minus lambda I? That means determinant of A is this much, then A minus lambda into I means 1, 0, 0, 1 will be considered. So that will giving you 1 minus lambda 4, 2, 3 minus lambda, right? So now its determinant, that is equal to 1 minus lambda into 3 minus lambda minus 4, AD minus BC. Okay, you get it, this one, lambda square minus 4 lambda minus 5 is equal to 0. This is the characteristic equation, right? So by Cayley-Hamilton theorem, it has to show that this equation is satisfied by A. That means A square minus 4A minus 5 into I, identity matrix, is equal to 0. So we have to show that A square minus 4A minus 5I is equal to 0. Now calculate that value. A minus 4A minus 5I. A square, A is equal to the given value. Then you find out A square, A into A. It is not just squaring. Understand, please. Usually people made mistakes very quickly like this. Multiply A into A. It results in you 9, 16, 8, 17 minus 4 into A, 4 times of A, minus 5 into I. It's very clearly it satisfies 0, right? So hence A satisfies its characteristic equation. So hence Cayley-Hamilton theorem is verified. Now the next part is finding inverse. So what from the Cayley-Hamilton theorem we drawn that A satisfies characteristic equation, that is A square minus 4A square minus 4A plus 5I is equal to 0, right? By Cayley-Hamilton theorem, we drawn this one. Now from this, we can find out inverse. Multiply, this is what only now, A square, sorry, minus 5I. Okay. So therefore, now we needed to find out the inverse. So that first multiply A inverse on both sides on this equation. It gives you means A minus 4I minus 5 into A inverse is equal to 0. From that we can write it A inverse is equal to 1 by 5 into A minus 4I, right? This is what we can find out. A inverse is equal to 1 by 5 into A minus 4I, that is equal to this one. This is the required inverse of the given matrix. It is very easy, right? And also now to find out another, there is no power now. Yeah, find A inverse only. Okay, then express this matrix polynomial as a linear polynomial in A. You see that expression we can take it. A power 5 minus 4A power 4 minus 5A cube plus 11A square minus A minus 10I. That is equal to, we rearrange this one in form of this terms if you made it. Okay, you factorize that one, we're getting that factorization factor as A square minus 4A minus 5I. A square minus 4A minus 5I into A cube minus 2A plus 3I plus A plus 5I. We can rearrange this one. Okay, we know A square minus 4A minus 5I is 0 because A satisfies its characteristic equation using the Cayley-Hamilton theorem. If 0 into this one 0, A plus 5I, this is the value is A plus 5. This whole value of the expression is just A plus 5I. So no needed to find out all these powers of matrices and simplifying this. Just it is simplified into a linear one, A plus 5I. It is very easy to find out, and this is same as this total matrix value, polynomial value. Okay, these are the advantages of the matrix Cayley-Hamilton theorem, right? Any doubt in this?
Sir.
Any doubt in this Cayley-Hamilton theorem? Yes, students.
No, sir.
Okay, let's move to the, there are many solved problems are there that verify the Cayley-Hamilton theorem, find out A cube, A inverse, and verify the inverse, the eigenvalues of A square or the square of the eigenvalues of A, and all of things. You find out the spectral radius. You know that what is spectral radius? What is spectral radius? Can anybody say? What is meant by spectral radius?
Sir, largest eigenvalue.
Right, right. Magnitude, right. Absolute value of the maximum eigenvalue. Yeah, that is what they have clearly finding. The given matrix, find out A cube, verify Cayley-Hamilton theorem first, find out the characteristic equation, and these characteristic, whatever what we can say, that eigenvalues, it is not needed, where the characteristic equation is this one. So you check it whether A satisfies this equation or not. You can very clearly showing that where it is not showing, it is clearly satisfies that equation. You can find out and show that one, and find out A cube. A square is equal to determine A square, A into A and A cube, A square into A. Okay, and then A inverse is equal to like this. Okay, it satisfies own equation, own characteristic equation. So therefore, from that itself, we can write it. We can find out the power of the matrix. A cube is equal to. So here it satisfies the characteristic equation, means A cube. Write it, minus A cube plus 3A square minus A plus 3 is equal to 0, right? So this is the characteristic equation. This equation would be satisfied by the own given matrix A by Cayley-Hamilton theorem. So therefore, from which we can write it, A cube is equal to 3A square minus A plus 3. Like this also you can calculate. No needed to multiply. Okay, and A inverse. So finding inverse, you just multiply this equation with A inverse on both sides. Okay, 3 into I, sorry. 3 into I is equal to 0. Okay, so therefore, A inverse become 1 by 3 into, okay, A square minus 3A plus I. Okay, so from this you can find out the inverse. Now eigenvalues of A square, you can determine. They are 9 minus 1 and 1 or plus 1. I need to check this one. I haven't done this. Just go find out this one. Okay, the spectral radius is maximum of lambda I. Okay, maximum of lambda I. These are the eigenvalues of A square. That eigenvalues of A are 3 comma plus or minus I. So therefore, maximum of lambda I is 3. That is the spectral radius. Okay, good. So these are the same, in the same way other problems are there. If A is equal to this much, then show this much and all. You do the problems, you can, all of them here, find power of the matrix has been given. Okay. If you have any doubt, you can, otherwise we will go into the next concept. Next, it is totally final applications of the eigenvalues and eigenvectors. One is diagonalization. Next one is mainly the quadratic forms, canonical forms, and solution of simultaneous equations that using the eigenvalue problem. Solving first order differential
Sir,
equation.
in that spectral radius, sir, how can we say that it is 3, sir?
Tell me.
Sir, in that spectral
Hello?
radius, how, sir, can... Hello, sir?
Spectral radius.
Sir, how can it be a 3, sir? Because since other ones are complex.
What is the maximum value in that?
Sir, but other are complex, so, sir, we can't...
That complex values cannot take only real values. Spectral radius, it will be a distance unit, so it must be a real.
Okay, sir. So, okay, sir. Sir, if say, sir, then lambda is coming only plus and minus iota, only two roots, means it is a square equation. So there will be no spectral radius in that question.
No, there may be one point only, that itself it gives the spectral radius. The set of eigenvalues will be the spectrum.
Okay, sir. Okay, sir.
Set of eigenvalues is the spectrum, and it is not the matter that how many number of points are there inside the spectrum. Okay.
Okay, sir.
Sir,
Hmm.
sir,
Right?
in the example you give the 1.6 example, the final equation that was in order of 5. How you resolve it?
Where?
For example 1.6.
Tell me.
Sir, the final equation that was in order 5, how you resolve it?
Degree of 5.
Yes, sir.
Hmm. So this we have expressed into factorized. We factorize this. We factorize that one. We factorize that one. How we can factorize that? We simplify the factors which needed the
Sir, we
coefficient
can divide it.
4a minus 5i. You see, this can be expressed into like this. Is it right or wrong?
Sir,
Ah,
so we can do in that way, na, sir. We can divide it and it can form quotient into that
exactly.
divisor plus remainder.
You just divide that one with it because it is needed the coefficient of a square. That means it must be the product of a square minus 4a minus 5y. Okay.
Okay, sir, now got it.
So that this value you know, that value you can put it 0 and the remaining it will be good.
Yes, sir.
Then anything? Okay, students. We will take up the next concept in the next class. That diagonalization that we will see in the next class. Okay.
Okay, sir.
Something. Would Narayan Rao need to say something? Narayan Rao?
Sorry, sir. Sorry, sir. No, sir. It accidentally raised.
No problem, no problem. If you want, you can discuss anything. Then, very good. So the three concepts are there, three classes. Next week we will be completing that one. You go through the concepts, the lecture notes which we have communicated. That almost mathematics 2 is to be completing by next week, right?